Modeling the human aorta is critical for understanding cardiovascular health. While microcirculation requires complex non-Newtonian models, flow in large arteries like the aorta is effectively described by the standard Navier-Stokes equations. Our model focuses on this Newtonian behavior, simulating the pulsatile pressure gradients driven by the heart, alternating between systolic pumping and diastolic resting phases. However, modeling this in a cylindrical geometry creates a significant challenge. That is, a mathematical singularity at the vessel center where standard equations fail. To solve this, we implemented a 1D finite difference solver that explicitly handles this singularity using L'Hopital's rule. This establishes a reliable numerical baseline, allowing us to accurately visualize velocity profiles throughout the cardiac cycle.
Our three objectives aim to model the 1D Navier-Stokes equation for pulsatile aortic flow using a 1D finite difference solver in MATLAB. This allows us to simulate laminar behavior and analyze the resulting velocity profiles and pressure distribution throughout the cardiac cycle.
Hi, my name is Owen, and I'll be discussing about the model settings for our projects. Since we're investigating and simulating the blood flow behaviors, we are setting our models in the descending aorta, where the blood is flowing along the aorta in a Z direction. So the model is based on two fundamental elements. First is the Navier-Stokes equations, and the second is the law of mass conservations. And after applying it using cylindrical coordinates, we can derive out the 1D blood flow model equations as shown in the right-hand side.
My name is Toka Peng with metric number 22004663. Now I'm going to present about the assumption made to model the Navier-Stokes equation. First one, descending aorta is a straight and rigid cylinder. Second, blood flow is fully developed laminar flow without radial flow and swelling. Third, cross-section of the aorta is a perfect circle to ensure its axis symmetric. The fourth one, no external body forces acting on the blood. Lastly, blood is Newtonian free in the aorta due to high velocity and shear rate. So we will get a final equation as shown at below.
Without pressure gradient, the blood wouldn't flow. So it is important to explicitly define the pressure gradient source term. Before defining it, we will make some important assumptions. First is there is a linear pressure drop along the descending aorta. Second is the pressure is constant at the exit at 90 mmHg. Thirdly is the Winkelser effect. In our case, is safely ignored. We assume there's no recoil effects when the blood is flowing and the heart is pumping. So in our case, the source of pressure gradient is the simplified heartbeat model represented in the equation as shown in the figure in the slide. So it is a summation of the average pressures during the diastolic stage and also a half cycle sinusoidal wave during the systole phase.
For the boundary conditions, no slip wall condition is simulated and there is maximum velocity slope at the central. Meanwhile, velocity at all points are set to 0 initially.
We also define the values of the parameters used in our model, for example the kinematic viscosity and also the aorta radius. For the P-mean and the A inside the pressure gradient system, we calculated it using the Hagen-Poiseuille law based on the minimum diastolic velocity and also the peak systolic velocity. Since we're using finite decimal method, we also define dr as 0.01 to balance between computational speed and also the accuracy. And time step dt is defined as 80% of the time limit, where the time limit is calculated using the CFL condition as shown in the figure below.
For the modal setting of pressure distribution analysis, the pressure gradient is uniform along the vessel segment. Then we determine the pressure at point z equals to 0 and z equal to 0.05, which is the middle cut of the vessel.
Table above shows the blood flow velocity from 0 to 20 seconds at different radial positions. Table below shows the pressure distribution at the inlet and the middle cut of the blood vessels from 0 second to 2 seconds.
Next, the pulsatile velocity profile of aorta is plotted against radial position in meter and time in second as shown in the figure. The result in blood velocity presents three important characteristics in blood flow simulation. The first one is a no-slip condition and wall interaction observed, where the velocity is maximum at the center of the vessel and decreases smoothly to 0 at the vessel wall, which results in a velocity gradient near the wall. Next, the smooth parabolic shape of the velocity curve also indicates that the flow region is laminar in the middle of the blood vessel. If the flow were turbulent, the profile would appear flatter with chaotic fluctuations. Besides, the velocity rises to a peak during the systole and falls during diastole, reflecting the rhythmic pumping of the heart. However, the result is lack of the characteristic of the short reflected wave. This is a limitation of our current model, specifically due to the rigid wall assumption and the backflow check logic in the code, which prevent the visualization of blood reversal.
I'm going to discuss the pressure distribution profiles from a perspective of pressure against artery length. As you can see from this diagram here, the pressure profile shape is actually of triangular pressure length enveloped with systolic and diastolic boundaries. Why is it triangular shape? It is actually due to the gradual downstream decay of pressure amplitude along the aorta. To point out some of the key characteristics from this model, the first one, why is it triangular shape? It is actually due to the monotonic pressure decay from the proximal inlet, which is the base of the triangle, to the distal end, which is the apex of the triangle. And it is also due to the superimposed pulsatile variation due to cardiac pumping. And this superposition of pressure, it is actually consists of two pressures. The first one, which is the temporally pulsatile inlet pressure and especially near linear pressure decay. To point out one quantitative findings that we found, the highest pressure actually it occurs at the proximal inlet with a gradual reduction toward the distal region while the pressure remains relatively uniform across lumen. When we see the pressure distribution profiles from a perspective of pressure against time, we can see that actually it is a series of periodic rise and falls events which are actually corresponding to the systolic and diastolic phases of the cardiac cycle. From this diagram, we can see there are actually a lot of systolic peaks that occur with an interval of 1 second, which is corresponding to one cardiac cycle, starting at t equals to 0.25 second with the maximum pressure at the inlet and the midsection of the model. As a conclusion, we have validated 1D, one-dimensional Navier-Stokes model by accurately simulating pulsatile blood flow in the descending aorta by having all the velocity and pressure values. And we have created a reliable hemodynamic framework by looking into the transient and steady-state behavior of the blood. Besides that, we also have found out that some of the future extensions that we can look into, namely vessel compliance, non-newtonial blood, and the pathological conditions of the patients.